this video, we're going to be looking at the logistic differential equation. The logistic differential equation is a much more sophisticated model to represent population growth. With population growth, many times we will have some constraints on the size of the population due to resources, diseases, and the amount of area we have. So we have what's called a carrying capacity. With just straight exponential growth, we don't have a carrying capacity. So if we looked at dp dt being approximated by k times p, this means if this represents our population growth for all time t, then our population would grow exponentially forever. Now, in a normal situation, if the population is small compared to its carrying capacity, for instance, if we had an island and we put 20 rabbits on the island, the carrying capacity of the island is maybe 100 or 500 rabbits. The initial population may grow exponentially, but as we get closer and closer to the actual carrying capacity of the island, the growth rate is going to slow down. So how can we represent the relative growth rate decrease as the population increases? This is where we add on this quantity 1 minus p divided by k, where p is the population and k is capital K is called the carrying capacity. Lowercase k is our relative growth rate. That's how fast our population is growing. But the capital K is our carrying capacity. For instance, if we had a growth rate of rabbits of 3% per year, that would be a growth rate, the relative growth rate. Whereas the carrying capacity may be 500 rabbits on the island. That's the carrying capacity for this island. Now, if we look at just that quantity, 1 minus p divided by k, we can see that as p gets closer and closer to k, p divided by k would be almost 1. Therefore, we'd have 1 minus 1 is 0. So as our population gets closer to our carrying capacity, our growth rate is going to be 0. But if our population is very, very small compared to our carrying capacity, say we had 10 rabbits out of 500, for its carrying capacity, well, that quantity is going to be very close to 0. So our growth rate is going to be close to k times p. So there we have identified all of the different parameters for our population. So this is our logistic differential equation. And we've discussed if p is very small compared to k, then our growth rate is going to be approximated by k times p. As p approaches k, as we get closer and closer to the carrying capacity, our growth rate is going to approach 0. Now, can we determine whether the function is increasing or decreasing? If the population of p lies between 0 and k, so with my example, if we have between 0 and 500 rabbits, our population should be positive, our population growth should be positive for values between 0 and 500, up to 500. However, if the population of rabbits exceeds 500, our growth rate then should be negative. Because then we would have p divided by k is greater than 1, so that quantity then becomes negative. So we would have a negative kp. We're going to look at the solution to this logistic differential equation, first of all using a directional field. Then we'll look at a problem involving Euler's method. Then we're going to look at solving this differential equation analytically. So the first problem, it says draw a directional field for the logistic equation with k equals 0.08, that's our relative growth rate, and our carrying capacity k equals 1,000. So we can plug those into our equation and then create a directional field. So there's our logistic differential equation with the known values plugged in. And now we could plot our small tangent lines at different or various points. So with this particular equation, we can see it's only dependent on P, the population. This is our directional field. This would be the directional field for this differential equation, which would allow us to look at the solution to this differential equation. Now, the solution to this differential equation would be the function P of t. And P of t would represent the population at time t. Now, this equation is called autonomous because the right side of the equation only involves P, the dependent variable, and not the independent variable. So the slope of the tangent lines is always going to be the same along a horizontal line. And you can see the slope of the lines, as we've discussed earlier, looking at the equation, that between 0 and 1,000, the slopes are positive, and the slopes are very steep when P is very small, and then as P gets closer and closer to K, we see that our growth rate starts to get towards 0. If we had an initial condition of 100, let's say we were talking about rabbits again. If we had 100 rabbits, our initial condition is T of 0 equals 100. We could then draw in our solution curve to the differential equation, and you can see it here in purple. Here's an initial condition of P of 0 equals 400. So this would be the solution curve for that initial condition. And here is an initial condition of 1,300. Now the carrying capacity is 1,000. We can see that the dP dt equals 0 at 1,000. So that's our carrying capacity. That's our equilibrium solution. So if we start out with more than our carrying capacity, the population is going to decrease until we get back down to our carrying capacity. Just a note, the slopes of these tangent lines are greatest at P equals 500. And there actually is an inflection point at that value. Now if we looked at Euler's method, here we have an example, the same example, we're looking at the differential equation, the logistic differential equation, and we're given an initial condition of P of 0 equals 100. Now it says use Euler's method with step sizes 20, 10, 5, and 0.1 to estimate the population sizes of P of 40. We can see it'd be unreasonable to use 0.1 to estimate P of 40. We would have to do 400 different iterations of that Euler's method, and we're not going to do that. But we could. I'm just going to actually show using Euler's method when our step size is 20 to evaluate one of these. And it would be the same if we use 10 or 5. We would just have a little bit more work to do. So let's look at, if we use Euler's method and we had our initial population of T equals 0, P equals 100, that's given as our initial condition, then we can find P of 1, which is P of 0 plus our step size times the differential equation evaluated at x sub or t sub 0, p sub 0, and that will give us our p sub 1. So in the first line we have p sub 1 equals 100, that's our p sub 0, plus 20, that's our step size, times f of 0, 100. That's plugging in 0, 100 back into our differential equation. When we do that calculation, we get 244. Now with that information, we can find P of 2. P of 2 would equal P of 1, 244, plus our step size times F of 20, because now we've taken a step of 20. So our X sub 1, or our T sub 1, would be 20. And our P of 1, we said, is 244. And if we perform that calculation, we get 539. Let's take a look at a table of values if we were to use Euler's method to calculate different population sizes. Here are the different step sizes. We used 20 for our step size, and we can see P of 40, we got 539. And we have different values of step sizes. If we use 10, you can see P of 40 would be 647. If we use the step size of 5, we get an estimate for our population of 695. And as the step size decreases, our answer becomes more accurate. So all the way down to a step size of 0.1, if we were to estimate P of 40, we'd get 731. Here's a graph that is going to compare the solution looking at the directional field with Euler's estimates. So here is a computer-generated solution curve for this directional field. Now I'm going to plot the values we got using Euler's method with our step size being 1. So you can see they're relatively close to one another, and it gives a pretty good estimate for the solution to this differential equation. Now we're going to look at the analytical solution to this differential equation. So if we solve this differential equation using separation of variables, we could rewrite this as dp dt equals k times p. If we multiplied this through, minus kp squared over k we would then have, if we got a common denominator, we'd have k times kp minus kp squared all over k. We could factor out a lowercase k. We have kp minus p squared so if we separate our variables, we would have, and I'm only going to bring kp minus p squared over to this side, equals our k over k, and then we would have our dt. Now, uppercase k and lowercase k are just constants, and we're going to find the antiderivative of both sides now. We're going to have to use a technique on the left side. We're going to create partial fractions so we can find the antiderivative. So if we take 1 all over kp minus p squared, and we factor the denominator as p times k minus p, we can rewrite this using partial fractions as a over p plus b all over k minus p. And then if we can find the values of a and b, we can plug those in and we have our partial fractions, and we can integrate that expression. So if we multiply both sides by p times k minus p, we would get so what we did there is we multiplied both sides times p times k minus p. So when I multiply it to this, the p's reduce and we're left with k minus p. When we multiply it by this, we're left with just p. And then when we multiply the left side of the equation, you can see the denominators would reduce. Now, if we let p equal k, we would have 1 equals a times 0 plus p times k. So b times k equals 1, so b equals 1 divided by k. And then if we let p equal 0, what we're trying to do here is choose a value that will either make this or this equal 0. So if p equals 0, we'd have a times k equals 1, plus now the b times 0 goes to 0, so a equals 1 over k. So we can rewrite this. Now we're going back to here because we found a and b. This could be written as 1 all over k times p plus 1 all over k times k minus p. We've created these partial fractions. That's equivalent to our expression, but now that will allow us to integrate this expression. So we've rewritten this as partial fractions right here, and this equals the integral of k dt. But I see that we could factor out this k from both of these. We'd have this 1 over k here, so that would leave us with 1 over p plus 1 all over k minus p dp. And I'm actually going to multiply both sides times capital K. So we would get the integral of 1 over p plus 1 over k minus p dp equals, now multiplying both sides by capital K would just leave us this. We can take the antiderivative of 1 over p, which is ln, the absolute value of p. Now, if we let u equal k minus p here, our du would equal negative dp. So it would be minus ln of the absolute value of k minus p. Then we'd have k times t plus our constant of integration. I'm going to use properties of logarithms to rewrite this as p all over k minus p and then if we raise each side to the, I didn't get the C, there we go. Raise each side to the base e, we would have e to the kt plus c. Now we're trying to solve for p. So we can take the positive and negative side to eliminate the absolute value. So we'd have p all over k minus p. And we're going to rewrite this as e to the c times e to the kt. And this would be our plus or minus. And we are going to replace plus or minus e to the c with a. So we'd have p all over k minus p equals a e to the kt. And again, we're trying to solve for p. Now I'm going to just invert both sides, just taking the reciprocal of both sides, still equivalent, because now we can solve for p easier. We could multiply both sides by p to get p all over a equals kt. And we're going to have to continue over here. So let's erase a little bit over here, unfortunately. So now we're going to subtract the easiest way to go about this from here, I think, would be to multiply. I think it'll look easiest this way. I'm just going to multiply both sides by this quantity, but then we would have to distribute. So we'd have k a e to the kt minus p times a e to the kt equals p. Now we need to get all of our p's on the same side. And then we could factor out a p. So we'd have p equals k a e to the kt all divided by 1 plus a e to the kt. I'm going to divide each term on the left side by a e to the kt. So that would leave k in the numerator. This would be 1 all over a e to the kt, and then we'd have plus 1. Now if we take this right here and just put it to the negative kt power, we end up with the solution to our differential equation. So we would have negative kt equals p. Now the 1 over a is just a constant, so I wrote that as our a. So this is the solution to our differential equation. Now we don't have to go through this process each time. We know that's the solution to our differential equation, so we can use this. To solve for A, if we look at our solution, which we said is P equals K all over 1 plus A e to the negative kt, and we're looking at time equals 0, and we're solving for this equation. If time equals 0, we'd be solving for our initial population, P of 0. So if we plug in 0 for t, we would get this. So P of 0 equals, now we're going to try to solve for A. So we'd have 1 plus e to the 0 is just 1. And so we'd have P sub 0 plus A P sub 0 equals K. And we are trying to solve for A. So A equals K minus P sub 0 all over P sub 0. That's how we get our value for K. So if we know our carrying capacity in our initial population, we can find the value of A. Here's an example. Write the solution to the initial value problem. Here's our logistic differential equation. We know the solution to our logistic differential equation. We just found it. And we are given values of K, lowercase k, and our carrying capacity just by looking at our logistic differential equation, because we can see little k is 0.08 and big K is 1,000. We have our initial condition, P of 0 equals 100, so we can just fill those into the solution that we found for our differential equation. We can calculate A. We just saw how A is calculated. We have K minus P sub 0 divided by P sub 0 is 9, so we can plug that in now. And there's the solution to our differential equation. We don't have to go through and derive this each time if we can memorize that form, K all over 1 plus A e to the negative kt. Now we can just plug in values. When t equals 40, we get 731. When p equals 80, we plug in those values and we can find the population at those times. It asks when the population reaches 900. That is our population at a particular time. So we plug in 900 for P of t, and then we would have to solve for t. And if we solve for t, we find 54.9. And that would be in years. Let's compare the natural growth and logistic models. We had a biologist do an experiment back in the 30s where he grew some protozoan and used the logistic equation to model the data. So find the exponential and logistic model for this data compared to the observed values. So here, if we use just the straight exponential function to model population growth, we would use this one, P sub 0 e to the kt. If we use the logistic model, we would use 64 all over 1 plus 31 e to the negative 0.79. Now let's look at the results of using the exponential compared to the exponential and the logistic. So at time equals 0, 1, 2 days, 3 days, 4 days, the actual population is the line labeled P, that row. L is the logistic differential equation. And you can see E just keeps getting bigger and bigger and bigger. And so that's not reasonable after 3, 4 days. It's not reasonable any longer. But you can see the logistic differential equation modeled it reasonably well. And here are the actual data points in yellow. And then we have the exponential model in blue and the logistic model in the green. There are other models for population growth. We have harvesting model, where if you have to harvest a certain number of animals per year, like deers, you have deer hunting. So they have models that they use to determine, well, how many deer need to be harvested per year. They could use this model. And here's another model for if a species population falls below some minimum value, they tend to become extinct, and they could use this model to model that population.